first some background on SIMD registers and instructions on PowerPC. There are 32 SIMD registers, each 16 byte, and 162 SIMD instructions. This is for Altivec. The newest versions of Power have more features. And there are also programmable prefetch engines so that the compiler can tell this prefetch engine, there are 4 actually, to load data into the data caches. But that's not of interest in this lecture. The normal types, except double, can be stored in the SIMD registers, and in addition, a special type called the saturated signed integer type as well. And what this means is that when, or actually instead of wrapping around when we try to store a too big number or too small, it stays, the value stays at either the maximum or the minimum, depending on what we did in this position in the SIMD register. Okay, one very useful instruction is called vector permute, and it takes 3 source operands, A, B, C, and produces a value in D. And what its purpose is to select bytes from vectors A or B. And it's not so that it only has to select 1 byte from A or from B, but it can select in any byte from either of these and put in a byte in D. That means we need to name the bytes in vector A and in vector B respectively. And the bytes in vector A are called, well, they are identified by 0 to 15, and in B from 16 to 31. Okay, so what we do is to write a number like this in a certain position in vector C, and then that byte is copied to the corresponding position in vector D. So say we have this content of vector C. At the first byte we take the byte called 0, which is here. So we write FF here. And then we take 16, so that's the one over there from B. And then we can write another one, the same. And then we write it 2, and so on. What can we do with this? Well, we can produce many operations. One of them is to shift 2 vector registers. And that is useful when we don't know the exact alignment when we read from memory. We will come to that next. So, vector load instruction, it reads from, it reads obviously 16 bytes, which is the sum of 2 general purpose registers, I mean integer registers. The interesting thing is that the 4 least significant bits are ignored from the address. And what that means is that the compiler must either know that a certain vector, I mean variable or an array in the program, is aligned. Not only the array, but actually the reference is aligned on a 16 byte boundary, or it must load 2 vector registers and shift. And this creates, I mean the second case, when it must shift, it creates a certain performance penalty. So, say we want to read 4 elements of an array. and we don't know the value of I, that means we don't know whether we can just use, say we have the address of A in R1 and the offset to the first element here that we want to read in R2. If we knew that this address, I mean R1 plus R2, is a multiple of 16, then it's sufficient to just load. But if we don't, what we have to do is to well, we can see it like this. This is the big array, and we want this, and this element. So this we want to have, but we don't know where this the multiple of 16 is located. So if we just load this, we will get the wrong value if we only take well, if we take the, say this is the boundary of 16 bytes, and then the next maybe here, for instance. So if we load this, then we will get the wrong value. We will never see I plus 3. So what we do is to load 2 vector registers, that one and that one. Okay, and so we do 2 load, 1 and 2, and then we create a bit pattern to shift, I mean to select the proper bytes from these 2. So V0 goes in here and V1 goes in there, and then we will shift using this vector permute and put so this will be vector 3, and it will contain exactly I and, well, I plus 3. That's what we want to achieve. That's what we use this vector permute to shift them a suitable number of bits. Okay, so how can we know in a very efficient way the bit pattern that we should put in this register? That pattern is it depends on the actual real address that we, virtual address that we I mean the address that we really have. But the term real address is used for physical address in IBM terminology. So let's say the virtual address. Okay, this instruction produces that bit pattern, and this instruction, the name is load vector for shift left. Okay, so what we see here is to load one vector, we need 5 instructions. That's a pity. What we can see is that if we are in a loop, then this one will be the same. I mean, the bit pattern that it produces is the same, but the source operand will be different. R2 will be 16 bytes ahead for the next iteration, but the value of V2 is the same. So that one can be moved out of a loop. And what we also can see is that this load in the next iteration is the same as this one. So there is actually only needed to have one vector load per loop iteration if we pipeline the vector load instruction. I mean, we reduce it in the next iteration. Okay, so this is details which affect performance. Now some add instructions. We see examples, vector add and signed byte saturate. There are also unsigned byte saturate. And well, there are all these saturate and modulo, that's the normal unsigned operation. There are numerous different instructions for each math operation.